Ready, Barry?
Yes, Rob.
3, 2, 1, fire. This is a linear induction motor. It uses about 100 kilowatts, and it can accelerate 4-pound missiles such as this up to nearly 100 miles an hour. Ready again, Barry?
Yes, Rob.
Fire. This is a big motor. On the other hand, in this thimble, I have the rotors of over 10,000 electric motors. And nobody is going to deny that these are small motors. Now, a linear induction motor like this is an easy thing to understand because it's just like a flowing river. This is a river bed. If I dip a piece of wood into the river, turn on the water, the first thing that happens is that the wood floats. It rises up, and then when the river is flowing nicely over the weir, I let go the wood, and it soon attains the same speed as the water. If, on the other hand, I dip into the backward rotation and something else. Can you see the spirals of filings running up the hill into the middle? The inward movement of these filings implies there must be an outward travelling magnetic field to produce it. And if this is true, then it's very exciting indeed, because centrifugal magnetism, which is what this would be, is unknown at present. But if we turn the handle more slowly and watch what happens in slow motion, we can see that the filings form into lozenge-shaped solids, and these are rolling over and over and spiraling into the middle, for the same reason that any rolling object traces out a spiral on a flat surface. So we hadn't made a discovery at all. But of all the phenomena we observed with the iron filings, the most striking perhaps is the building up of the walls. It tells us, among other things, that when we make a rack and pinion motor, we shouldn't use a solid cylinder like this. We should divide the cylinder into a number of discs. These 6 steel discs have been spaced to match the spacing of the walls in the iron filing experiment. They are going to wind up this cord, and in doing so lift a 2-kilogram mass. The discs will spin at 3,000 revolutions a minute. That is a lot of power to extract from such a small amount of material. In fact, that rack and pinion motor produces more power for its size than any other type of hysteresis motor. The shape of those discs is very similar to the shape of a coiled spring. At least it is magnetically. The most recent research that I've been doing has been concerned with rack and pinion motors of this kind, where we put a very small spring inside a glass tube, because this could operate as a self-contained pump, a helical pump. This spins very nicely, and of course smaller ones, being magnetic machines, operate better still. And I can spin this spring about 3 inches above the surface. Now, if I can develop these to the stage where they will be small enough to operate inside living tissue, then they could be very useful to the surgeon during operations. If this should be successful, then I'm never going to forget that it began with no more than a paperclip and a pencil. This, then, is the world of small motors. Now, I don't have to tell you that this is a big motor. In fact, in terms of diameter, it's one of the biggest made. Its rotor is this aluminium disc. So it's an induction motor, and therefore an electromagnetic machine. And in spite of the fact that the moving part is rotary, it is a test rig for linear machines. Let's have a look at the driving unit. This row of coils is a linear motor which has been bent slightly to fit the shape of the disc. The speed of the field on this motor is nearly 300 miles an hour. And motors of this kind are being developed to drive very high-speed passenger-carrying vehicles of the future. Now, to test such machines on an actual track would cost a very large sum of money. You'd have to build a track many miles long to get up to this kind of speed. But on this disc, we shall be able to get real speeds at the edge of the disc of nearly 300 miles an hour. So let's switch it on. Power on. But remember, whether it's a big, complicated piece of machinery like this, or if it's simply a paperclip and a pencil, in the world of motors big and small, the work you've just seen is only the beginning.